So, well, as we were discussing before, um, well, my idea for this presentation was to bring back the spirit of the group as a reading group. So I suggested a paper to discuss. And recently, in the work for my PhD, I have been working with probabilistic models. And well, on that work, it has led me into delving into a rich history in hydrological modeling. There's a very rich history of dealing with uncertainty and the things that you have to do to get probabilistic results. So from that side, it has been very interesting, but there's also, or something that always comes up, and something that at some point I also wanted to do was these topics of what is aleatoric uncertainty and what is epistemic uncertainty keep coming up. And I always knew that it was something that you could separate, that you get total uncertainty, and then you could separate it into these two things. And well, so the idea of the paper is to present these ideas, and well, the what these people from Oxford say is that this um, kind of this concept of having uncertainty as only aleatoric and epistemic is a bit misguided. So they suggest a different, maybe a different terminology for some of the similar things. So we'll get into their proposal a bit later. But I wanted to start just from the from a rough understanding of this kind, or what these kinds of uncertainties are. So I thought it would be good to start with an example. And this will be a very simple example where uh, I'll in an XY axis, I'll put some dots, which are supposed to represent data. And the idea of these dots are that uh, these particular measurements or whatever we have here represent these two clusters of complete kind of information that represents whatever is happening in this XY axis at this points completely. So if you were to, let me bring up my laser pointers. So if you were to say, well, I know that there is this phenomenon happening, and I was going to, and um, if these dots that are on the screen represent um, the whole of the outcomes that can happen, or the whole of the interactions that can happen between the X and Y in these two clusters, and we would be tracing a line around this data, then this is what we would call aleatory uncertainty. So it's something that is more related to the data itself. And then in this space, there's also this other side. If I remove the aleatory uncertainty, and if again you trace a line, there's these regions where we don't know what is happening between in those regions, in the regions that I'm marking on green. And this is what we would typically call epistemic uncertainty. So you can bring them together and they give you a picture of your knowledge of X and Y. So at certain points you have some observations, and as I said, because these observations represent all of the knowledge that, or all of the phenomena that can happen in these two particular regions, we call that aleatory uncertainty. And then in the regions where we have no information, there's this epistemic uncertainty. And if you bring those two together and there's some things that are missing, you can kind of marry the two and put them together in what can be considered a model. And as I said, the uncertainty of this model could be in principle decomposed into this epistemic and aleatory terms. So that's a very high level example. Um, while I was making these drawings, I thought, well, maybe I missed some things, but the general idea is that. So you have these two types of uncertainties. And the first one is aleatory uncertainty, as I said, which is typically explained as relating to chance. And it's associated with the statistical dispersion of the data and outcomes. And then there's epistemic uncertainty, which relates to knowledge. and it associates to the internal state of a particular model. So what the paper that I'm presenting today argues is that this dichotomy of epistemic and aleatoric uncertainty is a bit misguided. So what they propose is taking those and what they criticize mainly is one of a relatively famous PhD thesis by Gall et al., which is called Uncertainty in Deep Learning, in which he presents this view of aleatory and epistemic uncertainty. And well, the issues that they discuss in the paper is that these ideas are not being discussed currently in literature, and that there are different mathematical quantities that are used to refer to the same concepts, that there are misleading connections that are drawn between predictive uncertainty and accuracy, and there are assumptions that are made about how predictive uncertainty will decompose on unseen data. So the question the question that they answer why these issues arise is because these view of aleatoric and epistemic uncertainty is a bit too simplistic, and they, Smith et al., offer an alternative. So some key concepts before diving into their explanation of the normal view and the alternative that they propose, is that, well, first of all, you have to say that reasoning should start with the predictive task of interest. So in most cases where we have a predictive model, you're predicting y from x. But there for example, cases like generative model, you can also have a model that simply generates new outcomes. So there's no inputs, and what you're doing is taking outcomes from the model, so just taking y. And that already presents an issue to the epistemic and uncertainty, epistemic and aleatoric view of uncertainty. Then additionally, there are issues in, for example, that the training data doesn't need to correspond to a specific prediction. So if you have these XY pairs, which represent your data, the connection between X and Y doesn't necessarily have to be explicit between X and Y. So for example, you can have data that misrepresents Y as it could be predicted from X. So kind of disinformative data, or data that is not representative of what you're trying to model. Then you can use a model for data-driven predictions, and here they use this notation where, well, they say that the probability of y given x is the outcome of a model, and in this case they focus, or for this notation they focus on parametric models. So this notation that they use here is an expectation over all possible models given a certain set of parameters. So the parameters are typically sampled from a distribution, and they are typically, or you have a training data set which you calibrate the parameters with. And you could also have a space where, or you could bring together all possible models, and this would give you this irreducible, or the probability of x, or the probability of y given x based on all possible combinations of parameters. Then they go into this saying that the predictions, or having a predictive model is not the same as having described the data generation process. So because as the probability, and this is this distinction that they make between having a generative model and a predictive model. So these are two different things. And the last thing that they mentioned that is very important is that you have to have a reference system. So a reference system allows for grounded evaluation of the outcomes. So simply a reference that you can point towards, which has some sort of connection between X and Y. So this is the popular view that they are criticizing in this paper. And why they criticize it is because, as they say, when they use the terms aleatoric and epistemic uncertainty, it can refer to different things. So, for example, aleatoric uncertainty can be described as capturing as it captures the noise inherent in the observations. So, in that statement, it can be referring, for example, to the entropy of the training data, or it can be referring to the entropy of the reference that you have to evaluate. When they say cannot be reduced, even if more data were to be collected, then they are referring to this irreducible predictive entropy, which is kind of what you would. This is the most or the kind of definition that most reflects what aleatoric uncertainty is. So the irreducible predictive entropy. So if you have a set of all of the models and you cannot bring any more, then there's some remaining uncertainty that you cannot reduce. Question, you have a question?
Yes, just to clarify there. So there's several possibilities going on here. I just want to understand which one they are trying to describe. Okay. I've got a system, a generating process. I can assume that the rules of the generating process are fixed and deterministic.
Yeah.
And then I can assume that the parameters that inform those rules are fixed and deterministic, and that the entropy comes entirely from some kind of random process imposed on top of that. That's one possibility. Another possibility is that I can assume that the rules are fixed and deterministic. The parameters come from a random distribution, and there is no additional randomness added on top. And then the third is there's a combination of those two. The rules are deterministic, the parameters come from a distribution, plus there's a random process added on top. And then the fourth is that the rules themselves are probabilistic, and so on. I'm trying to clarify, based on your presentation here, which of those cases they're referring to.
And this, I think, refers to the second, or that's what sounded the most, where you have. So this would be the uncertainty that remains when you're not taking account the random process. So it's just the parameters in the
uncertainty in the
model.
parameters.
Yes.
Okay. So the rules are the probability distribution is known. It's just the uncertainty associated with not knowing the parameters that we're talking about.
And here, I think they also refer to the specific model class, because this P refers to a model. And when they use this notation of infinite, I think they're also referring both to the model class and the parameters of a specific model.
Okay.
Because that also comes with this conditional predictive entropy.
So the infinity includes all possible model classes?
Yes.
Can you say more about what they mean by a model class?
Well, I don't. Well, they focus on parametric models. So
would it be something like a first order model and a second order model? Would those be two model classes?
what do you
like a linear
mean
model and a quadratic model? Would those be two model classes?
Yeah, I think so.
And is there probability distribution over the model classes, or that's just multiple possible?
I think they would include probability distribution over the model classes.
Okay. All right. So the rules and the parameters are drawn from some known distribution.
Mm-hmm.
Okay, perfect. That helps. Thanks.
Okay. So that's the and I'm focusing on this term of cannot be reduced even if more data were collected as irreducible predictive entropy, because ultimately that's what they phrase what or how uncertainty should be viewed.
Yeah, it's what
And
Crutchfield refers to, I think, as the entropy of the data generating process.
exactly. So
Entropy
just
of
the
the data.
process by itself.
Yeah. Okay. So it's got some deterministic component, which is the part we would normally refer. If we don't know it, that's what we refer to as epistemic. And then we have the part on top of that that cannot be predicted with any rule. We can only say something about its distribution, and that we normally call the entropy of the data generating process. Okay, thank you.
Manuel, can I ask a question?
Yes, of course.
So one thing I don't understand, when the paper was sent out, I briefly looked at it, and I remember there are a few things I didn't like about it, and that's one of which I think I remember is that epistemic uncertainty in the model parameters. I'm not sure if I agree with that that's epistemic uncertainty, but
this is what they're criticizing. So this is or as it is presented in this thesis, and that's what they're
okay.
criticizing, is that it refers to uncertainty as the model parameters as the epistemic uncertainty.
Okay.
Yeah.
And so then the second question I had was, some of these terms listed here, for instance, P infinite y given x, and then the I assume is entropy.
Yeah.
You can never evaluate that term,
Yes.
right?
It's a theoretical term. Yeah.
It's a theoretical term.
You can estimate it.
Yeah. So you cannot find a consistent estimator for that one. Okay, good. Thanks.
Yeah. Yeah. So just as we did with aleatoric uncertainty, the terms are also confused when referring to epistemic uncertainty. So often epistemic uncertainty is used to refer to the uncertainty in the model parameters. So if we're keeping this notation of P of n being a model and then theta being a parametric model in this case, then the entropy of the model's parameters. And this is where they focus their attention to this second term of can be explained away given enough data when referring to the epistemic uncertainty. And later we'll see that they rephrase this can be explained away given enough data as the reducible predictive entropy. So this is, again, using these theoretical terms of a single model being referred to as P of n, and all possible models being P of infinite. So this is the what remains if you take a model like the total uncertainty of a model and reduce whatever aleatoric uncertainty is, so of the process itself, nothing from the model, and then you get this reducible predictive entropy. So yes.
So I'm trying to relate this to Jasper's work on misspecified models, just to keep us in the same page. Does P infinity assume that the set of model classes includes the quote unquote true model, whatever that might be? Do you know?
Let me check.
Because if it doesn't, then Jasper, then that your model misspecification issue means that you can't explain it away given enough data. Right? Yeah.
Yes.
Yeah, I can't find where they define it.
Okay, never mind. We'll just keep that in the back of our minds. Yeah.
Okay. Yeah, so this is the typical view and how this is explained. As I said, what they criticize is that these different terms are used interchangeably when referring to any of these quantities. Well, so they propose an alternative, and the alternative is mostly based on information gain.
Sorry, could you go back just one more thing? So on the left side, you got h of p infinity y given x. And in principle, that's the smallest entropy achievable. Am I correct?
Yes.
Okay. On the right, you've got h of p of n, and oh, I see. Okay. The first, yeah, I was misreading it. The term in green is larger than the term in orange, and so
Yes.
that's the difference. Okay, and then the expected value. Okay, got it. Thanks. This is very interesting. It's related to something I've been thinking about recently too. Yeah.
Yeah. So they, for their alternative view, that's exactly what they do. So that's how they suggest that these two types of uncertainty should be evaluated as the uncertainty that you can actually reduce and what is actually irreducible. So you start from a point of total uncertainty. So there's the total uncertainty base for a specific model. And then you can decompose it into whatever is the remaining uncertainty, so whatever you cannot reduce. So if you had the infinite set of all models, there would be still something that cannot be explained by this infinite set of all models, and that's the remaining uncertainty or the stochasticity of the process itself. So that's from your model, that's the part that you can always subtract, and what remains is your so what remains is the uncertainty of the specific model or what you would eventually be able to reduce from the model. So so the term of that you cannot reduce is basically given by the total minus the irreducible. And that's what they explain by, or how you can reduce it. They propose that it can be reduced by information gain. So the information that you gain by collecting more data. So they propose this more kind of intuitive view of the total or of these two types of uncertainty as whatever information you can gain based on collecting new data. It would be something that is only part of the total uncertainty that is not irreducible. So, and well, as Jasper said, these are theoretical terms. So they propose these two ways of estimating these quantities. So they propose that the irreducible uncertainty can be estimated as this expected entropy, expected predictive entropy given a certain model's parameters. So kind of like one realization from the space of model parameters. And that would give you, it's an estimate, so it's not the real thing, but it's an estimate that gives you some sort of idea of the amount that you can reduce the total uncertainty, that you cannot reduce the total uncertainty, sorry.
Total uncertainty of the prediction.
Yes, exactly.
Okay, not of the parameters.
Yeah.
Okay, or the model, right. Okay.
And yeah, so this idea of, and I think up to here, so then when they say, well, you can estimate those things, they go into why you can estimate those things with a certain number of propositions that they make. But I think that's just more getting into the details. I think the idea of having a certain amount of uncertainty and being able to decompose it into something that you can reduce and not reduce up to this point in this figure, it's valuable, and I think it's easier to understand if you use those terms of reducible and irreducible than the terms of epistemic and aleatory uncertainty. So that's the main point of the paper.
So what they're calling irreducible is what we normally would call aleatory, and reducible is normally what we would call epistemic, but they're trying to be more precise about
Exactly.
the definitions. Because when Wei and I worked on this way back, we pointed out that what is aleatory could be still reducible if you brought more information, for example, additional variables or something that you needed. So if you're missing variable, what is actually epistemic would appear to be aleatory because, right? Okay.
Yeah, I tried to go back to the paper by Wei Kong and through this view, and I think it's part of the same issue that they point towards, that there's things that get often mixed up between the different terms.
Right.
So I think you have to, while you're reading, don't not maybe trusting the words, but just what the actual quantities that are being calculated, and then bringing them back to these two ideas of irreducible and reducible.
No, I like this. I'll just point out that the problem that we pointed out in that paper still remains, which is it's conditional on X. And so it's conditional that on the fact that you have a certain amount of information.
Yeah.
And even the irreducible uncertainty there could be reducible if you had more information about X in principle. So that ambiguity in the equations remains, but not in the definition. I like the definition.
Yeah. In the example that I was showing at the beginning, I saw exactly the same issue. So that's why I was trying to be so clear in saying, well, these points that we have in this region completely describe what it's happening in that specific region, because otherwise you can still have.
But yeah, I take slight issue with your picture. If you could go back to it.
Okay, it's here. Yeah.
Yeah, I know it's meant to be illustrative, but your solid green line implies that there is no epistemic uncertainty inside the data, and obviously that would not be true too. So, but I like the cartoon polarization of it as a way of thinking about it. Right. Yes.
Yeah. And well, continuing with this example, you can see, and this is maybe here is where it's more what you might be thinking of. So as they suggest in the paper, you can replace these two terms of aleatoric and epistemic into reducible and irreducible. So what we would traditionally call those two things. And from this point of view of gaining information, then you can modify this small cartoon by, for example, adding two more data points, and then you can correct what your epistemic or what your reducible and irreducible uncertainty might be.
Yeah.
So that's more probably what you were thinking of. And yeah, so
no, I was actually thinking of the fact that you have another dimension of X. So you've got a missing variable Z.
Okay.
And if you don't observe Z, then when you plot X and Y, you get the scatter. But if you plot Z, that scatter reduces. That's what I was talking about. Yeah.
Okay. Okay. But well, this 2 points in the middle, I think describe what they're what they're suggesting, that these two types of uncertainty should be viewed through the lens of gaining information by adding more data. And well, that's most of the presentation. Well, the takeaways from the paper are mainly that this traditional view of aleatoric and epistemic uncertainty suffers from some problems, and that's what the authors discuss. They propose an alternative, and they stress this separation of uncertainty into irreducible and reducible. And instead of relying on this aleatoric and epistemic dichotomy, the author suggested the composition that is based on a model's total projective entropy that can be decomposed into irreducible uncertainty. And here, irreducible uncertainty will remain even, or it remains even if you add infinite data, and reducible uncertainty, which can be reduced with more data. So that's the main takeaway of the paper. And yeah, that's the presentation. It's a short presentation for this week. But thank you very much for your attention.
Very cool.
Thank you, Manuel.
So the thing that still sticks with me is that there's somehow the idea that the data contains information without viewing it through the lens of some kind of model. And we talked about that at the information theory workshop, if you recall, that there's somehow this idea that the model independently adds information, the data independently adds information, which of course is not true because you can't interpret the information, the data, without throwing it against a model. So I'm trying to see how that enters into this. I think over here, this assumes that you have a full model class that you can draw from and upon which you can impose a probability distribution on each possible model and model class. And in reality, you have to estimate those probabilities from the data.
Mm-hmm.
So you end up with this chicken and egg loop, right? Unless you use something like Solomonov's universal probability, which has something to do with description length. So longer, you have to impose some kind of prior probability on your model classes.
But well, maybe I was thinking about something similar in terms just of database modeling. So as we mostly do with neural networks, and I was questioning myself if when you use a database model, what your result is only the aleatoric part. If your model is perfectly, like, it doesn't interfere in the data that you, or it completely it's it's in complete agreement with the data that you have. And if, because you're using a database model, then what the remaining component that you have in your uncertainty of the outcomes is only the aleatoric part.
So you're assuming, based on Kolmogorov's theorem and some simple assumptions about smoothness and continuity, you're assuming that the underlying function can be arbitrarily accurately approximated by a machine learning representation. Yeah.
Mm-hmm.
Yeah, that makes sense.
Yep.
The other thing that you didn't point out, I didn't read the paper, but was they're assuming a fixed data set and they're not sampling from the distribution that generates the data, or are they? That's what I
They
was.
do work with limited samples. So when they say n is based on a certain number of data points that they have.
So they're not reflecting in their in their calculations the fact that you could have gotten a different sample of the same size. You know, you used years 1 or year 2 or year 3 or year 4
Mhm.
or whatever. And because of the limited sample size, you potentially could you potentially could think that the irreducible uncertainty is smaller than it actually is,
Mhm.
because you're overfitting to that
Yeah.
particular sample, right?
Yeah, I think that would fit.
So Manuel, so what we about 20 years ago or so, so in my PhD work, I was very interested in exactly this topic, and after some thinking and literature study, I realized that if you want to estimate aleatory uncertainty, that the best way of doing so is not to use a model at all, but just look at, if you look at discharge data, we have the underlying signal is relatively smooth. So if you have hourly data, for instance, even daily data for some catchments, then you can actually show that you can estimate the measurement error, the random component of those variations in discharge. You can actually estimate that directly from the signal itself. So that gives you an idea.
Mhm.
It's basically the same way. How would you get an estimate of the variance of your, you have a temperature sensor, right? You want to get an estimate of the error. You just measure 10 times every second, right? You get 10 different readings. That gives you differences, right? And then you get an idea about the measurement uncertainty.
It's still a model,
And
Jeff.
Pardon?
It's still a model, though. I assume it's I assume it's perhaps a better model for estimating it, but it's still a model.
Yeah, that you directly get it from the data about the short-term fluctuations in the data.
Yeah, but
And that gives you one of the terms there, right? That's the aleatory uncertainty. That is just the measurement error essentially of the discharge data. And that works beautifully. You can show that mathematically. You can, there are three, your signal needs to be sufficiently smooth, your underlying data generating process, right? Now that's true with discharge, unless you're in a very flashy catchment where you go from 0 to high peaks and that many times. But so yeah, so there are certain assumptions, but in other words, for a lot of the data that I see people work on, they're not aware of this approach. It's model free and it's really easy to do.
There's no such model free, Jasper. That's my point. It is still a model. It's a database model. And it's basically what Gray was pointing to when he said that you can get a bound, a close bound on the estimate of the uncertainty by using a database model instead of a physically based model, because you still have to fit a model through the data based on.
No, you're not fitting a model. You're not
Absolutely
fitting any model.
Absolutely you are.
No, you're just taking the difference between two data points, right?
That's a model.
Yeah, but I wouldn't use the word fit. You said you're fitting a model through the data. I wouldn't. Yeah, okay.
Yeah, but you're taking a difference, which is you're saying I'm going to do 1 times x2 minus 1 times x1, and the parameters are 1 and 1. It's still a model.
Yeah.
You could have done 1 times x2 minus 0.9 times x1, and you would get an autoregressive model, and so on and so forth. Yeah.
Yeah, you just take you're not using any autoregressive scheme or anything. You just take the difference in adjacent data points, so difference operator.
That is an autoregressive scheme.
Yeah, but you're playing with the coefficients, right? I'm not playing with the coefficients.
No, I agree.
So yeah, so you can call that a model. I just call it model free still. It's just data based, but
I think of it as the simplest possible model or a simplest possible model. The reason
yeah, it's
the
yeah.
reason I'm saying this is because I'm trying to characterize how we talk about the description length of a model, right? And what you're talking about is essentially what's done in compression, where if you can find a trend in the data, right? So if you take streamflow and you just do the differencing of the data, and then you store the first value of streamflow, and then you store the differences, right? And you look at the description length of that, that's shorter than the description length of the original streamflow data set. I've done it. You can show that it's true. Okay. Because
That's not intuitive.
sorry?
That's not intuitive.
It is
That
absolutely
is
intuitive.
shorter. Oh,
That's
not
what
for me.
that's what it means to have a trend. Right? That's how you compress data files on a computer. You look for patterns in the data, right? And you apply those patterns, and then you store the pattern plus the residuals.
Yeah, but in your example, if we have a discharge time series, right, and we start differencing, then the
Yep.
differenced vector, it has one element less than the original vector. That's why you said that you store the initial value.
No,
Then you
yeah.
still store the same number of data points, right? So that to me is not clear that why that would be shorter.
Because the basic fundamental assumption of measuring length is that small numbers are shorter than large numbers.
Okay. So you're not storing everything as a
Yeah. So the description
view.
length is log normally related to the values, right?
Okay.
Sorry, is logarithmically related to the values in bits. Okay.
Okay, so that I understand. I was wondering whether you took the length because you mentioned you store the initial value, but the length is the same, but the values are smaller on average.
The number of values is the same,
Yeah,
but the amount of
but they're
storage
smaller.
the number of bits you need to store it on your computer is smaller, right?
I agree, yeah.
And that leads to compression, and that leads to why we look for patterns, right?
Yeah, so the reason I responded to you, Hoshin, is in part because my student also has given talks several times about this way to measure aleatory uncertainty. And people in the audience, most of the time, they're just really confused. They still think that we first fit some underlying model through the data, some very smooth underlying model, right? But you don't do that at all. It's only data-based. And I think that to make that switch to people, it's called the field non-parametric statistics. They have a whole field that does this type of stuff. It's very interesting, just because it gives you also what to expect with machine learning, right? It gives you a lower bound of how far you can go.
I've always agreed with the approach. I just don't agree that it's not a model.
No, but that's why I'm trying to avoid to use the word model, because the audience gets confused. They actually think that you fit some high. That is why I'm trying to avoid that word.
The simplest example would be, let's say your data generating process was y is equal to mx plus c plus an error. Okay. Just simple regression line. And you store y plus z, which is y plus the error. Sorry, x and z. Right?
Yeah.
Then you know that you can reduce that, right? You only have to store x, and you have to store m, and you have to store c, and you have to store the errors. But what is m? M is just that differencing.
Mm. Yeah.
M is dy by dx, essentially.
Yeah. No, yeah. So in other words, it's, I think for a lot of us work with data sets where we have a lot of data. I just never see that differencing operator to get this low. It's very, people don't really use it. Whereas with machine learning, it gives a low bound. By the way, one thing I've been talking to I think it's the right place now maybe to ask you. So I don't do a lot with machine learning in terms of running large machine learning models or so. I look much more at the theory. But what I do know, and this is because I have some colleagues in, that are more physics and statistics and mathematics, and we discuss things, they bring things up, they send interesting papers. And one of which is that turns out that if you have a neural network or so, LSTM or whatever, that there's now recently, and this has been research for linear regression. So when you make the network increase, you make it more and more complex, and then you look at an evaluation data set, it will get better and then it will get worse. It will continue to get better in training, right? And then it starts deteriorating. The more complex you make, it starts deteriorating in evaluation, right? But there is another hump, meaning that it will get worse initially, but that doesn't mean it won't get better when you continue to make it more complex. And that has to do with the neural network, with the construction of the network, the local minima, I think what they call it, the real set of solutions or so, so that it can get better again when you actually continue to make it more complex. But we always stop, right? As soon as it gets worse, we stop. But there's actually now a paper on this using linear regression where people show and come up with an actually analytic insight why this can be. And this has to do with regularization. When you train the network, that for certain complexities, the network has a lot of decrease of freedom, but if you make it even more complex because of regularization, you actually make the network perform better again out of the training phase. So I don't know if anyone has researched this yet, if you're familiar with this, that you can have this second hump, that it gets better when you make it more complex, continue to make it more complex. I don't know if any of you is familiar with this, but I thought I'll just mention it.
Yeah, typically it's when the degrees of freedom in your network are larger than the amount of data that you have.
So yeah, so I thought it was really interesting. But again, that all is conditional on this regularization, that you force the weights and biases. Because if I have something called the Runge phenomenon in polynomial fitting, right? That if you keep adding polynomial terms, higher order terms, that you start oscillating, right? But then that happens because there's no constraint on those polynomial terms, on the coefficients they carry. But in machine learning, if you apply that regularization constraint, that the sum of the weights needs to be 1, or the sum of the squared weights is whatever, that actually can make happen that you get better again with increasing complexity. First gets worse and it gets better in training. I thought it was really interesting. Anyway, there's a linear regression proof that people show that this can happen for linear regression. So
there's a lot of regularization that goes on implicitly in machine learning, which is what people are studying now. One of these is that you always normalize your data on a unit cube. That's necessary for the proofs to work. And because of that, when you sample your parameters from your network, you always sample from something like a Gaussian distribution with values that are very close to 0. And so you're implicitly already regularizing the network, even without putting constraints on the parameters. You're implicitly regularizing because you're starting your search in a place very close to the origin. So there's a huge number of these kinds of regularizing things that people are talking about that go on when we do machine learning, which apply over and above the fact that you might add constraints on the values of the parameters and so on. So implicitly, you've already put a preference on the parameters that they need to be close to 0, for example.
So you make sure that the weights by using normalized inputs, not standardized, but normalized inputs between 0 and 1, that that's also right. The weights and the biases, right? That you don't have an issue there, because if the inputs vary orders of magnitude, then you can have issues with your weight initialization.
So that's the first thing. Then the second thing is if you search in a very high dimensional space, only a subset of that network might actually end up predicting the output. So a lot of those weights are irrelevant. But it's kind of like you're converting global search into local search by expanding into a very high dimensional space. You remember we talked about this a long time with Jasper, where if you project it down into a lower dimensional space, it starts to behave more like a multi-local optimum problem. Whereas if you expand it up into a high dimensional space, it starts to behave more like a local optimum problem. And there are a lot of techniques in math now where you always expand up into a high dimensional space first in order to be able to use simple techniques, and then you project back down to a lower dimensional space. They seem to have this property too, that they make the problem easier to solve.
Right. I came in late, sorry, but I might add cross-validation to that list, just because a lot of regularization, right? You're trying to get a better estimate of out of sample performance, which is exactly what you're doing with cross-validation.
Yeah, so the thing, Tim, that we were talking about is that there's evidence that when you make a network more and more complex, that your performance can improve again. So, but we already stopped training by then. Because it already deteriorated, and then we stopped. But if you continue making it more complex beyond that you can actually start improving again in the evaluation period, cross-validation.
So think of it this way, Jasper. Let's say you've got a one-dimensional problem, and you keep improving as you change theta 1. And then you get to a point where it starts to get worse. Now add a new dimension, theta 2, and ask, what does the response surface look like now when you got 2 parameters? So now you've got 2 degrees of freedom to move in, and you could now move in some combination of theta 1 and theta 2, which actually goes down. And then you could add a third dimension. So theta 1 and theta 2 now start to go up. And now you add a third dimension, and now you can have a new dimension in which theta 1 and theta 2 and theta 3 actually go down.
Yeah. So no, I understand all that, but I don't think there are many papers in the literature that explore this double hump, right?
I don't know about many. I mean, I've run across quite a few.
No, but I'm talking about the hydrology literature.
Oh,
That
in
they
the
continue.
hydrology literature, nothing. No, absolutely.
No, that's why I bring this up.
Sure.
Because I think most people are not aware of this.
Sure.
They continue with the complexity as soon as it starts deteriorating. That's my point. Look beyond that, because there's now also, because people didn't understand this. This was reported in machine learning, and people didn't really understand why this would be. And then this linear regression example came, I think, by the son of Tipsy Rani. They published in 2021 or so an example with linear regression showing why this is the case. They could explain this.
But at what dimensionality were they able to show that? For low dimensional problems or for only high dimensional problems?
No, these were, I would say, still relatively low dimensional problems.
Like what? When you say low?
I mean, it's linear regression. So I have to go back to the paper, but it's no, we're not talking about the order of magnitude with machine learning, right? Where we have hundreds and hundreds of weights and biases. That is what is reporting in machine learning literature with deep learning.
No,
they were able to demonstrate.
Machine learning is talking about millions and billions of parameters.
Yeah. But okay. So that's certainly not dimensionality. It's just simpler linear.
But I'm not sure about if it's the same phenomena, because there's this idea of double descent, which is I think what you're describing, and I'm not sure if that happens when you grow the model in complexity, but is just by keeping training on the same data set for a long while. Eventually, you reach this point where a double descent happens, where you start to overfit at the beginning, but then you go down again. And I think it's related to what Hoshin was saying, where at the beginning there are certain parts of the network that may not be being used at all. And then if you keep trying to exploit the data, you reach at another configuration of the model where you're probably able to find a lower minima. Or yeah, in terms of complexity, I'm not sure if I have seen something like that.
It's very
Yeah, so we're talking about
bound to
the
the
evaluation
problem.
phase, right?
Sorry?
We're talking about the evaluation
Talking about the
performance, right?
evaluation, yeah.
Yeah.
There's a fundamental problem with the standard evaluation phase, which has always bothered me, and that is you break the data into two parts. Let's ignore cross-validation for a minute, but let's say you take that you break the data into two parts, okay? And you calculate F1 on the first part of the data, and you calculate F2 on the second part of the data, okay? So now you have a multi-objective problem, okay? And you imagine that each of these data sets has a quadratic response surface, but this data set has its minimum here, and this data set has its minimum here. Yeah. So we're going back to multi-objective optimization. And now you know that there's a Pareto optimum that joins these two minima, right? Okay, so I've got two circles. I got a circle here and a circle here. Sorry, I should have a piece of paper. Okay. Okay. All right. Now, if your data was completely consistent, your model was completely consistent, these two would overlap very closely and you would just get one minimum, right? Okay. Now, let's say I start my search over here. Okay. So I'm going to, and this is training, and this is the training one, and this is the evaluation one, right?
Mm-hmm.
And I search this way, and I get there.
Mm-hmm.
Both training and evaluation are going down. But evaluation is higher than training, just by my construction. Okay? Now I start my search over here. And I take this path. Training will keep going down, but evaluation will start going up.
Yeah.
Okay? So you have a generic problem with this approach of splitting into just two portions of the data, right? This is somewhat mitigated when you do stochastic gradient descent because you're picking a different portion of the data, and so you start to get something where the response surface looks more like that, right? Okay. When you do five-fold cross-validation, you get 5 of these guys. So you end up kind of in the right ballpark, but depending on where you start, you're going to end up somewhere else, inevitably, right? And we almost never start our algorithms multiple times and explore the entire Pareto optimum, right? So this is something that's bothered me for a long time. It's okay because all you care about is a better model. But if you're trying to talk about optimal models, then you really have to take this issue into consideration, and you have to bootstrap from your data, and you have to you have to end up looking for the entire. I mean, you've done work on this, Jasper, where you end up with a probability distribution of solutions where you can't know exactly where the correct solution is, and it's sort of basically related to this Pareto optimum problem, right? Yeah.
But
Yeah, that's good, Hoshin. Yeah. Sorry. Last thing I want to say is that one thing I realized now I'm doing much more statistics is that one of the things we don't really look into, which is really important in the context of epistemic error, etc., is people are very focused on the objective functions themselves and the performance, but they do not look into the consistency of the parameter values. Essentially, we want to use training criteria, whatever you want to call it, where you need the shortest amount of data and as small as possible to find
Shortest what, sorry?
consistent parameter. Pardon?
Jasper, you're
What do you
breaking.
say? Ah,
You
can you hear
broke
me
up.
again?
Could you say that again?
So essentially, so I've been doing a lot more statistics like in the last few years. And when I talk to my colleagues, they always talk about consistency, consistent estimators. They talk about, convergence speeds and all that. And so one of the things we don't really do, because I think this relates to what you also mentioned, is that we don't really look at consistency of our parameter values. And so ideally what you want is you want to have scoring functions or whatever metrics, right? Where you need the shortest amount of data to get consistent parameter estimates. That's essentially what you're looking for, so that you have a tremendous convergence that you need 10 discharge data points, and then you get the right parameter values, and it doesn't matter whether you use them this year, next year, they always converge to the same. And I find in the literature, you published a paper about this, Hoshin, in I think 1985 or so, when you looked at consistency. So it was more theoretical, but I think that is an issue that we don't really look into too much, but that's a really important aspect. I think if you look into epistemic uncertainty and all that, the consistency of the parameter values, because this dates back to what you just described, that also has to do with consistency, because now you're interpreting the parameter values, with training and testing, and you want to make sure that you arrive at more or less the same values, irrespective of where you start. Yeah, but again, if it's machine learning, people don't care about the parameter values, right? If it's a prediction, who cares, right? I'm only interested in a prediction, but I think to get the better, deeper understanding, it's important to look at the consistency of the parameter values.
And just to make sure I'm on the same page, by consistency, you mean the variance of the parameter values?
No, just their optimal values. Yeah. I mean, their variance is one aspect. So that when you repeat your analysis, that you arrive at more or less the same value. So I don't know if people have done this with the KG, the NSE. It's easy to do. Like what happens, what parameter values, what's the relation between the length of the data set, etc. Because for the RMSE, those standard metrics, this has all been shown, right? That this works when n goes to infinity, this is, etc. You converge to the pseudo true parameter values, etc., etc., etc.
I think Richard Vogel has done a little bit of work in that direction, or quite a bit of work in that direction, looking at.
But I don't know if he looks at the parameter values itself.
Well, he talks about the consistency of the estimator, not so much the consistency of the parameters, but I think that's
what
the
we're
point.
talking about here.
Yeah. And fortunately, we now have people like Tim and others who are taking statistics a lot more seriously. I mean, I'll just be honest, but when I got involved in all this, my statistics background was zero. And, we're a bunch of hydrologists who just sort of adopted the minimum amount of statistics we needed to help us write a paper and solve our problem. We didn't start out as full-blown statisticians, so we made a lot of shortcuts and so on along the way.
Oh yeah.
I can relate.
Yeah, for instance, yesterday, how do you estimate, if you ever thought about this, a 95% confidence interval? We usually take off 2.5% on one side, 2.5% on another side, but that is not the smallest 95% confidence interval. You can construct your interval differently, where you not necessarily take away 2.5% from one side and 2.5%, as long as where you have the cutoff, they have the same posterior density.
Right.
Then it's okay. So in other words, I was talking about this also in the context of this Bayesian model averaging. That's the normal way of doing it. But you can construct smaller intervals where they're not symmetric, where you both leave out 2.5%. Anyway, point is, I'm talking but even a lot of statisticians are not necessarily aware of these things. They're very well trained.
Sure.
But I mean, I'm talking about the same issues today with a colleague of mine. We almost talk every week, and he really knows a lot about all this stuff. And we're still talking about the same problems 20 years ago. We made some progress, I think,
Sure.
but we still talk about the same problems, essentially.
Well, I have to say I partly blame the statistics community because they focus on um, there's a very strong tendency to focus on theory and advancing the theory. And unfortunately, a lot of statistics departments around the world have been axed, more and more. There used to be a statistics program in the University of Arizona. It doesn't exist anymore.
It's terrible.
And if you take a statistics course, they want you to focus on theorem proving and this, that, and the other. And I don't give a shit about that. I want to know what the ideas are and how do I apply them, right?
No, you're right.
Right. But I have a different question for Manuel because I thought there was something early in your presentation which rang a bell with me, and you didn't go back to it, so I was a little curious. I've been thinking a lot about the difference between understanding and prediction, right? The difference between building a model for understanding and building a model for prediction. And I'm curious, I have some thoughts on it, but before I say anything, I'm curious what you guys think would be some of the fundamental differences between building a model for understanding and building a model for prediction. Are they the same? Are they different? Is one conditional on the other? How do you parse this out?
I don't think that would be that different. As for complexity, like that, there is a bunch of frameworks with which you can do equation discovery. So that would be increasing understanding instead of prediction. And those, I think, are highly dependent on the complexity of the model itself. I think that applies as well with physics-informed machine learning, which is more prediction focused rather than understanding, but uses the understanding part for regularization. I think it's just a hot take. I don't know how right is this, but I would say the complexity factor is going to be the main slider you want to move right there. So like the size of the network, number of layers, the overall complexity of what you're trying to model, I would say.
Representationally, do you think there's a difference between saying that I have developed understanding, given some data, versus I have developed an ability to predict? Representationally, are they the same or are they different? What do you think?
Probably
Because
different.
if they're the same, then you could buy the machine learning argument that if I can do great predictions, that means I have great understanding, right? But I don't buy that one, so.
No, I guess the difference would be between in-distribution prediction and out-of-distribution prediction. Actually, I wanted to touch on that based on the reducible uncertainty that was shown. And I was going to ask Manuel if there is some sort of link with out-of-distribution prediction with machine learning and what are the implications with that. So I guess my answer would be the biggest differences probably would be observed in the out-of-distribution sampling and prediction. I feel like if you have a model that understands and a model that predicts right, the in-distribution prediction will be rather similar, but generalization out of distribution is going to be fairly different. And with that respect, after Manuel's presentation, I'm wondering if those results on epistemic uncertainty are just another proof that out of distribution is extremely hard or impossible to achieve, even though this is the reducible part. If that makes sense, Manuel, maybe you can.
This is not discussed in the paper, so they
Yeah, but
or how
what are your thoughts on this? I mean,
no, I would agree that yeah, it would definitely, it's something that outside of distribution, yeah, yeah, You would have to think that if you're training on a limited data set, then outside of that training limited training data set, then the epistemic part will take a lot more relevance.
I think it hit me when you had this slide with how can you reduce it, well, more measurements. But the thing is, if you're when you're fitting that distribution training a model, you don't know where the other data points will show up. I mean, I'm working with extreme weather events and everything I mean, what we know is what we've seen so far. But every year, like there are bigger fires and bigger problems that we can't really predict because they never happened up to this point. So I guess in that context, it's that question. Out of distribution is what we have not seen. It's counterfactual. So how do you make the difference between more measurements? Like when we have more measurements in the future, once those will have happened, where can I hypothesize those next measurement will be? Hence, how can I reduce my out of distribution, which is that epistemic uncertainty. And I think like that's part of the problem. And maybe relating back to Hoshin's question, that would be the difference between an understanding model and a predictive model. Predictive is going to do great today. Maybe an understanding model, so physics-based or something else, is might be able to do better for the future as well and predict more out of bounds and out of distribution. Now, how to achieve that is another question, but theoretically, yeah.
That's a very fundamental question. It's a very good question, Hoshin. A very good question, because I sometimes I'm sure you do all talk to those people as well, like working on climate and all that. And they talk about these teleconnections, and they still don't really understand how these teleconnections work. And then I always tell them, if I was a farmer in the Central Valley and someone could give me a prediction of winter rainfall that is based on the number of bikes in New York in October, how many bikes there are in New York, then I would listen to that person if that's the best prediction. But in climate, that's not accepted. So empirical teleconnections, if you data analysis from the past and you find teleconnections, that is just very hard to publish. They want to know the physical, they want to have a model that you can, understand what's going on. And I think in some sense that hampers progress. So I think in education, Hoshin, you want a model where you can, if you teach, you want a model, right, that's built on understanding. But I think in machine learning, a lot of people are not, once you master the understanding, I guess, then the next step is that you go to machine learning to get even a better prediction, assuming that you understand the material. But I find it hard to tell you what the difference is between the two. Because ideally, it would be the same thing in an ideal world.
So you guys are giving me lots of ideas, but let me tell you where I'm sort of sitting at the moment. Manuel put up the distinction between a generative model and a discriminative model, right? And my argument would be that the generative model is closer to understanding and the discriminative model is closer to prediction. In other words, the generative model is asking, what is the relationship amongst all the variables? And it doesn't care about the direction of the relationship, right? If I've got two variables, x and y, the generative model is the probability distribution of y and x. And if I give you y, you can tell me something about x. If I give you x, you can tell me something about y. Maybe not perfect, right? But there's some underlying relationship between x and y, and then there's the epistemic portion added on. Sorry, there's the entropy portion added on top, right? So I would argue that when we're trying to build understanding, what we're trying to do is close the loop on something which says the function of x and y is equal to 0. We're trying to make the right-hand side of our relationship 0. And when we're doing a predictive model, we're trying to say y is a function of x. So y minus the function of x is equal to 0 is what you're trying to do. And that's a one-directional relationship. It means if I give you x, I can tell you y, but if I give you y, I can't necessarily tell you x. So to me, that seems like generative understanding is in some sense omnidirectional or multidirectional amongst the variables. It feels to me like understanding is hierarchical. So you can look at things at different kind of scales and resolutions and so on, and still say something about the relationships amongst things. And it feels to me like understanding is also multi-representational. It's like you can take the same data and you can build a decision tree-based model, or you could build a recurrent neural network, or you could build a different kind, a convolutional neural net or something. You could build, and each view on that somehow gives you a different perspective about what's happening underlying or underneath. So when I think of somebody as having understanding, it seems to me that it allows me to modify the questions and still be able to get some answers to them. Whereas in a predictive model, you can't change the question, right? Or you're much more limited in your change of the question. You can't look at it from multiple perspectives and so on.
You can't change the context, at least.
Yeah. And I've got a little illustration here that made me think of that. So I know that a linear reservoir can be described by this autoregressive process. Q of t plus 1 is 1 minus k times q of t plus k times p of t. I can derive that if you need to, but if not, k is the conductivity coefficient on the tank, right? And if I rearrange the terms, I can show that you can do q of t plus 1 minus q of t over p of t minus q of t is equal to k. Okay. So if I take my data, which consists of p of t, q of t, and q of t plus 1, and that's my attention window, and if I somehow manipulate it through a neural network so that the output, regardless of what data I come out with, is a constant value, k, right? It's not going to be. If you do it with real data, this won't happen unless the data really came from a linear reservoir or this generating process. But if I get that, then I can say the function of p of t, q of t, and q of t plus 1 is equal to 0. I can actually close that loop. There's no entropy on the right-hand side, right? And if there was some residual entropy, then it would be that the entropy would exist on the right-hand side. You wouldn't be able to close it to 0. You would come to within some short description length. But in this case, basically, I don't have to represent the errors at all, right? And so that's what made me think that understanding is more closely related to trying to find the manifold in the data space and describe it somehow, as opposed to the predictive model, which is trying to do q of t plus 1 is equal to 1 minus k times q of t plus k times p of t, right? And then I do z of t plus 1 minus q of t plus 1. Right, where z is my observations, right? Now q is my prediction from my model, not my observations. In the other case, all three were data, right? But now it's basically And then I'm trying to minimize the entropy of this ET plus 1. This is actually a very trivial example, and actually it boils down to being almost the same, right? Minimizing E and minimizing the randomness of K ends up being more or less the same. But I think it's kind of illustrative of what we're trying to do. In this case, it's a very simple case, whereas in a very complex system, the manifold can warp and bend in very complex ways. And learning the data generating process learns how that manifold warps and how to describe it, right? Because when I ask you a question, if I say the stream flow in the river is so much today, can you tell me what the rain was? You can kind of answer it, right? There's a kind of a way in which, right, I give you partial information and you fill in the gaps. And I sort of try to me, that feels a lot more like understanding. And the reason I brought this up is because it sort of appeared briefly in your presentation, I thought, Manuel. And we, I'm just wondering if we haven't pursued that avenue enough. It's like, what would I do if I put the data into a neural network and I said, calculate some function of this data and generate an output. And now I train my output to be as small as possible, the entropy of my output to be as small as possible. Right?
I think you can do that with some of the equation learning frameworks.
I think that's what they do.
Yeah.
Yeah.
Yeah, for a group presentation with Praveen in the group, we built a small equation discovery. I think it's a regular neural network, and the point was just to learn basic bicarbonate and other carbonate equilibrium in the system. So we just fed it synthetic data, and we were able to make it converge to the original set of equations. And basically, that's how you do it. You set up the equations as regularization terms and ask to optimize for 0. That's how it works. So that would be maybe interesting to try those frameworks with real data and trying to figure out some equations with it. Because once you get the understanding part, you get the prediction part.
So I'm curious, if you gave it data, if it would learn a relationship between PT, QT, and Q of t plus 1 that is not reducible easily to this equation, right?
So Hoshin, there's another aspect, I think, that with a predictive model, that implies calibration, and a model for understanding does not need calibration.
Maybe, because I'm still training this parameter K.
Yeah, in your example.
Yeah. Or I'm discovering this parameter K. Whether you call it training or discovering, I don't know, but it's just, but it's an interesting point, right? Because maybe you could feed in data to a neural network and you would be still learning the weights. But you're learning the weights that when you combine everything together, outputs 0. Does that make sense?
Yeah.
It would still need to be a training process because you still have to discover this functional form.
But when you describe hydrology in class, right, you go over these linear reservoirs and then conceptual models. That's a level of understanding how water flows from A to B through a watershed. There's no calibration involved there. Whereas with the predictive model, you need calibration, otherwise the model is useless.
But the question I'm asking is the following. If I gave you QT, PT, and QT plus 1, and you fed it into a neural network, and it learned this relationship.
It learned K in your case, yeah. Or it learned the relationship.
It learned that I have to take QT and subtract it from QT plus 1. I have to take QT and subtract it from PT. I have to take the ratio. Okay. And then it gives me a value of K, and that value of K is constant at every time. Let's say that's what my neural network learns for me, right? It looks for the shortest description length explanation of this data, and that's what it comes out with. Now it gives me that equation, and now I can go and manipulate that equation and ask, how do I get a predictive model out of this? It might not be this relationship. I'm just making this one up, right? It's the one that made me think of it. But in general, the neural network will come out with something else. Like if you pass this through a Kolmogorov neural network, it would come out with a whole bunch of transformations and so on and so on. And it would say at the end, here's my shortest description. Here's the representation that gives me the answer that's closest to 0, right? This would be like your equation finding algorithm, Antoine, right? Except that here I'm using neural networks. I'm not doing symbolic logic or anything like that. I'm just using standard operations like multiplication, division, functional transformations, exponentiation, anything that a neural network could do.
Well, I don't have any guarantee or promise, but if you can generate data out of that, I can try. I'm not guaranteeing anything, but we made it with H2CO3, HCO3, and CO3 relations
Okay.
at steady state. So just pH controlled all that, and it works pretty well. So I don't guarantee I'm gonna be able to hatch something up, but we can definitely try. I mean, there is no harm in trying, I guess.
We could give you the leaf river data. There is an issue here where I'm telling you that the only 3 data points I'm giving you are Q of t, P of t, and Q of t plus 1, right?
Yeah.
A more general problem would require me to choose an attention window of some size.
Okay.
Yeah. And vary the attention window and keep doing it, and each time come out with the best answer I could get. So it'd be a
Unknown caller.
it'd be a sort of a recursive discovery process, but I could give you leaf river data and we could try it.
Yeah.
Right.
So this reminds me also of the work that Peter Young did, right? On database mechanistic modeling.
Absolutely. You're going, yeah, I love his work.
Yeah.
Okay.
Because I think you're hinting at the same thing, Hoshin, is that machine learning is really easy nowadays, right? People just throw data in, something comes out. But I think it's really important to have discovery before that. And this is the discovery before that. What do I feed to the network? What do I expect the network to do? Like a deeper data analysis before we undertake any PyTorch or so. Push a few buttons. Yeah.
Just
But I would still think, though, that for me personally, but I may be wrong, that the model for understanding is not necessarily a good model for prediction. And that there is definitely a strong component of calibration involved in a predictive model, which in my view, a model for understanding doesn't need.
Yeah, I mean, in this case, because I constructed it that way, I can reorganize my terms to get Q of t plus 1 on one side. In a general formulation, that won't be easy for me to do. And so I might have to do simplifications in order to get at prediction from understanding. That's what I'm speculating, right? But it's also possible, Antoine, that if you started the entire discovery process many times, you might end up with multiple possible, discover multiple possible relationships, and then you might have to parse through them to find the one that allows you to separate out the terms most easily, right? So there could be multiple possible explanations, but we end up choosing the one which is most convenient for us, or something like that.
So there's one other thing I wanted to share with you briefly. That is that I came across some work that was also sort of shared with me by some colleagues that essentially, so all these neural networks have they're wonderful, but they're computationally intensive. They have a lot of local minima, and they're very difficult to interpret in terms of understanding. So there is a theorem that says that every neural network, well, call it an LSTM or whatever you want to call it, that you can approximate that with a kernel-based function. So once you have your final network, you can approximate that behavior with the kernel representation. And the kernel represents, it's like if you do spatial interpolation. I'm not talking about geostatistics, but let's say you do nearest neighbor interpolation, right? That is the same idea. But that is really well interpretable because you can look at the distance, you can get much better ideas about the relationships in your data. So that is what I've been looking into.
Can you send us that paper, Jasper? That looks very interesting.
I can actually maybe present it. It's a very short paper. It's a very interesting, it's a theory with a proof, relatively easy to understand, where this author a few years ago says that you can actually derive that kernel-based representation from the gradient descent of the neural network. If you keep track of all the parameter values and the gradients at every single step, that from that information, you can reconstruct the kernel-based representation of your machine learning model. So I'm now going through that. That is not 50 pages, just 2 pages, simple idea. And I found that because that allows us, if we can find kernel representations, those are much easier to interpret. They don't have the issue with local minima.
Sure.
So there are many, because everyone is diving on these neural nets now, right? But there are other possibilities. If you go back in the literature on neural networks are just one type of machine learning. There are many other type of approaches.
Yeah.
So I've been working on this a little bit because I'm still finishing some other stuff on this misspecification.
By
that
the way,
was the next step, but I can.
You may be interested, Jasper, that there's another paper which actually does something similar, but shows that you can reduce any ReLU-based neural network to a decision tree.
Yeah. Yes. So those type of papers, I think for us, we should maybe discuss this because I think that offers really interesting alternatives, which are much better to interpret, easier to train. So yeah, that's what I've been looking into.
What do you think about presenting on July the 30th? That's the next available slot.
Yeah, that should be possible.
Yeah,
I mean,
okay.
I'll be in Europe somewhere, but that should be
All
fine.
the same.
You know what? I'll put you in the schedule for now. I'll reach out to you for details later on, and if you want to postpone a little bit or something, we'll figure it out. But
no, sure. You can put me in there. Yeah.
And stick me in to talk about Wolfram's multi-computational at some point. Yeah.
Yep. You already have something on June the 18th, but that's LLM focused.
I forgot what that was about.
This is a PNAS paper. How should advancement of large language model affect the practice of science?
Oh dear.
I think that's the summary that you... It's the summary that you sent recently, I think.
Okay, I'll have to dig it out.
Yes.
I've got so many different directions recently.
Yeah, all right. I can see you another date.
Sure. No, that's fine. I'll figure it out.
Okay.
Oh, we can change it, I'll see.
Jasper, the paper that you refer to, is that the Radford Neal paper or is it another one?
That's another one.
Okay. Radford Neal is another classic where they prove a Gaussian process is equivalent to an infinitely wide neural net, which is sort of a...
Yeah. No, that's interesting. Yeah, very interesting. Lots of things going on. And,
I have to think about, I mean, again, I'm not a mathematician. I would consider Gaussian processes as sort of a kernel-based approach, but there might be a technical distinction that I don't know. But one thing I've found that I really like about working with Gaussian processes is that it's much easier to work with sparse data sets in fact, like a lot of our data sets are pretty sparse, and often we're using some sort of statistical model to interpolate everything into a nice complete grid that then gets fed into our neural net. But like, stream flow is an example. We don't measure continuous stream flow. We just have sparse measurements of flow and stage. Or, when we look at water quality, we often don't measure that continuously. We just have these sparse measurements, and it's really hard to use those. At least you all might know better, but I'm not aware that there's like off-the-shelf approaches to using those sorts of data sets with neural nets. But with like kernel-based approaches, Gaussian processes, it's trivial. It plugs right in, and it's very nice.
That would be useful to understand if you could give us an explanation of that.
Oh, yeah,
concepts underneath it. Yeah,
I have a manuscript, a prospectus I'm about to submit, so I'll share that in a few days if you want. I could talk about it here too. I can sign up on the sheet, I guess.
So
I'm busy with this other paper about.
Sure. What I'm hoping is that we can keep the underlying thread of information theory.
Oh, okay.
And but I consider these to be part of that thread. I just want to make sure we keep it clear, because when I say information theory now, I don't just mean Shannon information and algorithmic information. I really mean what I've been trying to talk about, which I'm just using the term representational information. In other words, there's a way in which our representational choices help inform us, right? Information in that sense. So our representational choices are in principle arbitrary, but they're not arbitrary. They're ones that serve us in some sense, right? And Shannon was talking about how do you represent things where you can only describe the large scale structure, the population structure. You can't describe the individuals except through conditional distributions and so on, right? Population structures. And Kolmogorov was talking about things that you can describe by deterministic algorithms or rules and descriptions and relationships. And it feels to me like what we're more concerned about is how you put all of that together and build complex representational descriptions of things. And then when we do that, we end up having multiple choices about how we can do that, right? That speaks to the discussion of prediction versus understanding. If all you want to do is prediction, you just find the representational choice that gives you the most accurate predictions. But if you're trying to do understanding, then you're choosing the representational choices that somehow allow you to answer other kinds of questions other than what's the next value in the sequence, and so on. So to me, it's still part of information theory, but I keep trying to say, how do we build this theory that I would like to call representational information theory? What are its elements? Yeah.
So I got really inspired recently by work from Alan Hunt. So he works on percolation theory. And yeah, it's fantastic work because he's able to tackle some of the most difficult problems in hydrology. And based on very simple theory, he's able to explain relationships at different scales. And so that and my own reading of some work by others have made me come to realize that I think, like in computational science, they use network models. Everything is based here on information theory, Shannon. And what they show that with these network models, that you have emergent behavior coming out of these models. And I firmly believe that physics is all emergent behavior. So I believe that the physical laws are not encoded or so.
Okay, you're going to like the discussion of Wolfram then.
So that they're actually emergent properties And I think in hydrology, for some reason early on, maybe because of our engineering background, we chose to have physical models of hydrological systems. Whereas we could have chosen a different path with these network models. And I think that is at least, that's my internal own conviction. I may be entirely wrong, but I started all coming together for myself. I was like, in the next 10 years, I want to really start focus on these network models because they have all the aspects of the discussions that we're having. And it's all still based on information theory. And I think that then the hydrological laws are emergent properties of those network models because they're still in all these physics-based models, they don't have emergent behavior. Whereas we know that our systems, they self-organize, right? That's not in our models. So interestingly, there's this professor in Amsterdam, his name is Peter Sloot, and he's done a lot of work on this, but in other fields. And then he explains that nature is not chaotic. I mean, it's partly, but it's not chaotic and it's not deterministic. It is on the boundary of the two. And he argues that at that boundary, you have the best flow of information. The flow of information is most efficient. That's why nature operates exactly at that boundary. If it's complete chaos, you don't have the patterns that we observe in nature. If it's entirely deterministic, you would have one species that would dominate all the other species. So you have variability. So it's a combination of those two. And it turns out that his research had found that at that point, you have the flow of information, the way information is processed is most efficient. And then he dates this back to the Fisher information. And so now the whole circle is closed because I've done a lot of work on this Fisher information. So that's why, for me, that's all coming together. I think in hydrology in the 80s, the 90s, our pursuit of physics led to these physics-based models. But by doing so, we removed a lot of stochastic behavior from our models, right? It's this equates the same as the ideal gas law that describes the behavior of a gas, because we can describe the individual molecules. So you get emergent properties such as pressure, temperature, and that works beautifully for a lot of these molecules, right? But these network models allow us to introduce much more complexity and pathways. And it's all still based on information theory. So I'm internally convinced that that's something, a direction I want to go. And leave the physics-based models to the side, because I think they, they have their limitations, as we all know.
Jasper, I don't remember if you were on the last one, but are you aware of Kramer-Rao bound?
Oh, yeah.
Yeah, when you're talking about, I mentioned it in a past call, but when you start talking about consistency and variance of estimators and Fisher information, it's like, yep, it all comes together in Kramer-Rao.
Yeah, if your model is correctly specified.
Well, then you have, right, then you achieve the bound.
We know that that's not true.
Then you achieve the bound.
Right.
If it's not, then you just have a greater variance.
So, yeah. But it's interesting, because when I talk with Peter Krumelt, so because going back to what you said, Hoos, about statistics, right? Is that they prove certain things,
Go ahead,
but it's only for a limited class of functions. It's not for the generic, like the safe base and all that. That all works if it's linear regression. If it is very simple relationships, then yes.
So it's interesting you're talking about that, because almost the first thing that he says in this report over here is that, the progress of science from thinking about, back in the Greeks and so on, things as elements and you can deduce things by reasoning, to the mathematical representation. And he points out that basically physics emerged based on this paradigm that everything could be described by mathematical relationships. Yeah. And then he goes on to the 1980s, the emergence of the computational paradigm, which is based on the recognition that there are things that are representable using computation that cannot be described by equations. And there are things that are represented by equations that cannot be described as algorithms. And then there are ones that can't be described by either equations or algorithms and so on. Anyway, it just occurred to me that what you were saying about the nature of physics is very closely related to that. Yeah.
Oh, thanks. That makes that what I said for the first time in my life made some sense. Finally. Okay, good. Yeah. Oh well. I'm an amateur, right, compared to these individuals. So
So we'll have a discussion on that because I'm really looking forward to it. I think it's interesting how people critique Wolfram. They think he's got a big ego and he doesn't cite other people and there's a whole bunch of things. But he definitely puts out some very interesting ideas there. Like he doesn't submit his work to peer review and all this kind of stuff. So a lot of physicists actually hate him. But he makes a lot of comments. And then I'm thinking back to Kevin Knuth, who we invited to our first workshop, information theory workshop. And he also was trying to showed in one of his papers that you could derive the laws of physics by starting from objects and relationships, basically from information theory. So there's more and more, there's more and more of this kind of thinking emerging, that there's something more fundamental than physics, right? That physics is an emergent phenomenon of something that you can call information. Yeah.
I mean, it's so what Wolfram has done. It's mind blowing if you think about it. How you teach your computer? I mean, just one aspect, right? But how do you teach your computer to do integration for you? Because then you really have to think deeply about the mathematics, the underlying rules, right? That's really, I mean, the same as ChatGPT of the abilities it has already. I mean, it's remarkable what I was asking ChatGPT yesterday. Can you tell me what the expected value is if I draw samples, the expected value of the squared value of the samples from an exponential distribution? And it just writes it out. You need to verify that, of course. But imagine 5 years from now. And then if you ask, hey, can you explain this to me, right? And then he will explain all the lines one after the next. So you don't need to, if you have a daughter or son that needs to goes to school, has a question, now ask your GPT. Can you explain? I mean, it's unbelievable, right? There's progress. It's changes education completely. What do we teach our students, right?
All right, guys, it's 12 o'clock over here.
Yep, it's a good conclusion. I'll
Been
stop
a
the
wonderful
recording here.
discussion.
Nice
Thank you,
talking to you.
Manuel.